Welcome to the course on signal processing for music applications. This week we're talking about the sinusoidal model. In the theory lectures, we actually presented the model and we presented it from a signal processing and mathematical point of view. In this demonstration class, I want to present it from a practical point of view, so actually using it. So let's go directly to the SMS Tools GUI. And let's start with the DFT model, and let's open one sine wave, this sine wave at 440 Hertz. Okay, so let's listen to that. Okay, so let's use a Hanning window, that's fine. Maybe let's use a window size of 511 and maybe an FFT size of 1024. We compute it. Okay, so this is the sine wave, the magnitude phase spectra, and the reconstructed signal from the spectrum. The sinusoidal model will attempt to find the peak, the spectral peak, the height, the location, and the phase corresponding to that location. Of course, it will do it for the whole sound, so it will start from the STFT. So if we get the same sound and get the same type of parameters, 511 and 1024, and let's just put this half of that window, and this will be the STFT and the spectrogram. We listen the output. Great, pretty good. So in here we are seeing this red line, which is basically the peak as it evolves in time, which is very stable, and in the phase we see this clear area, which is the flat phase of the main lobe. Okay, but now let's go to the sine wave, the sine model, and let's do the same thing. Let's open the sine. Let's use the same parameters, 511 and 1024. And now we're starting with the parameters that are specific for a sinusoidal analysis. For example, we have the magnitude threshold, which is the magnitude threshold in decibels that we're going to be looking for. So we're going to be looking for peaks that are within 50 dB from the 0 dB from the maximum of the sound. We can restrict the duration of the tracks. For example, well, let's just put 0, so no restriction. We can restrict the maximum number of sinusoids, 150 is plenty. In fact, there is only one. And we can restrict the deviation from frame to frame in terms of how this track evolves. And here we have put 10 at the lowest frequency. And then normally it's good that this deviation changes as the frequency goes up. And as the frequency goes up, it's good to increase this deviation. So this is the increasing factor of this deviation as the frequency goes up. Okay, so let's compute that. And okay, interestingly enough, we are seeing more than one line. Okay, there's resynthesis, we can listen to that. That's pretty good. It's a sinusoid. But in the analysis, here we are only seeing the frequency values of the peaks. We are not seeing the magnitude or the phase. So there's 4 lines, but clearly they may not be the same amplitude. So where do these come from? In fact, they come from the side lobes. We specified a magnitude threshold of -50, and if we go back to the signal, the DFT, and if we zoom into the peak, well, we're going to see that apart from the main peak, there is side lobes that are peaks and are within 50 decibels of the maximum energy. So therefore, these have been picked up. If we want to not pick up these side lobes, we should reduce this threshold, for example, -20. And now there is only one line. Okay, let's complicate this and let's analyze a little bit more complicated signal, for example, 2 sine waves. So let's go back to the DFT And let's get rid of all these windows, and let's open the sum of two sine waves, 440 and 490 hertz summing together. And let's maybe well, we have to choose the window size appropriate for a specific window. And we talked in the theory class that in order to do that, we can use an equation that says that it has to be the number of beams of the window, in the case of Hanning window is 4, times the sampling rate, which is in this case 44,100, and we have to divide it by the frequency distance that we want to resolve, in this case between 440 and 490 hertz, so 50 hertz. Okay, so this number 3528 is the size of M, the minimum size of M, if we want the two main lobes of these two sinusoids to be separate. So if we put here 235, and we'll put it as an odd size, so we'll put 3529. The FFT has to be bigger than that, a power of 2, and let's just analyze at this point. Okay, and now if maybe we zoom in into this region, we will see, okay, the two peaks of the two sinusoids. Okay, then we'll do the sinusoidal model, we'll do the short time Fourier transform. Let's go directly to the sinusoidal model, and let's put the same values. Let's get the sum of these two sinusoids, which maybe let's listen it. Okay, and now we can set up the values as 3529. Okay, and again the FFT size 4096. And okay, the rest of the parameters, let's lower the threshold. I think minus 20 maybe is a little too little. Let's just put minus 30, for example. Okay, and let's leave the others the same as we had before. Okay, let's compute that. Okay, and now we have the original sound and the resynthesized. We can listen to that. Okay, that's pretty good. And if we zoom into this area, okay, we see the two lines, the 440 hertz and 490 hertz. What happens if this size is not large enough? For example, what happens if it's 1800? And of course, we don't need such a big FFT. Let's 2048 is sufficient. And I think in here, let's make sure that be safe, and let's have a lower threshold, let's say minus 40, and let's leave the others the same. Okay, and now we see something interesting. Okay, so if we listen to the output sound, it's not that bad, but if we look at the analysis, it's definitely very different. Okay, if we look at the analysis, okay, what we are seeing is kind of it gets confused. Sometimes it finds 2, sometimes it doesn't. So clearly, we don't have enough resolution for discriminating clearly these two sinusoids. Even though when we sum it all together, it doesn't sound that bad. Okay, but anyway, we'll have to pay attention to this and make sure that we understand how the parameters have to be set for analyzing specific types of sounds. And now let's go to a real sound. Let's use the oboe sound, and let's go directly to the oboe sound, which is it's the note A4 at 440 hertz. So let's calculate again this the distance that we need to, the size of the window that we need to have. Maybe let's change the window, and let's put, for example, a Blackman window. Okay, what should be the window size for this sound? Okay, the Blackman window, the number of beams is 6. The sampling rate is the same, 44,100. And now we have to divide by the fundamental frequency. The fundamental frequency of this sound is 440 hertz, and that's the distance between two consecutive harmonics. So we will put 440 hertz here. And this is the size that we need, 601 samples. Okay, so let's put 601 samples. FFT size, well, let's put the next power of 2. And now, of course, we are dealing with a big sound that has a lot of harmonics, and they will go pretty much down. So let's put a bigger threshold, so lower value. Okay, so let's put minus 80. And now we can, these parameters matter a bit. So there might be spurious kind of tracks. So let's get rid of tracks that are small. So for example, 0.05. So we get rid of that. In this case, now we will need quite a bit of sinusoids. And we definitely will need this deviation. So this will be a deviation that will be quite useful. Okay, and let's compute it. Of course, it takes longer because it's a much more complex sound. Okay, and this is the result, the original sound. The tracks, here we only visualize in the first 5,000, but if we would go higher, we would see more. And we see pretty good all the horizontal lines. And of course, here at the end, there may be some harmonics that are disappearing. Let's listen to the original and the synthesized. Okay, that's pretty good. What happens if, for example, the threshold is not low enough? Let's put minus 30, for example. And let's recompute it. Okay, now what we are seeing is that it has not been able to capture all the harmonics. The harmonics that were too soft were not analyzed. So let's hear what we got back. Yeah, clearly this is only a part of that sound. And that's basically what I wanted to talk about. So this was a class that I tried to introduce the sinusoidal model from a practical perspective. And of course, we have used the SMS tools, the GUI, and these sinusoidal sounds that we have, and the oboe sound we have been playing around with come from Freesound. And that's also, hopefully, that has given you a practical view on the sinusoidal model. Of course, this requires for you to practice quite a bit more. It's very important to analyze many sounds and to actually see what is the effect of the different parameters on different sounds. And in fact, that's what we're going to do next demonstration class. So I hope to see you in next demonstration class where we will actually analyze a more complex sound and go into the sinusoidal model more deeply. So see you next time.